Okay, so the question I want to explore is how many rigid motion symmetries of this pentagon are there? So imagine this pentagon is regular, even though my drawing is terrible. And in particular, I want to ask the question of how these symmetries relate to each other, particularly algebraically. So what do I mean by rigid motion symmetries? Well, imagine picking up this pentagon off the screen and playing with it and then putting it back. So doing stuff like rotating or flipping, so reflections, and putting it back so it looks the same, I'll consider that a rigid motion symmetry. Okay, so let's just jump in. The first thing that we can consider is rotations. So let's denote by R the rotation or the action of rotation counterclockwise of our pentagon by 360 degrees over 5, which is 72 degrees. And we want to visualize this, but R is a rigid motion symmetry by my definition. So let's picture this by drawing a couple of pentagons. And the first thing I want to do is label the vertices just so that we can see what R is actually doing. So let's label these 1, 2, 3, 4, 5. And then R just rotates the vertices around 1. So 2 is on the top now, it goes 2, 3, 4, 5, and then 1 is on the left. Okay, not too difficult. But why stop there? We could rotate twice, for example. So that's just basically applying our first rotation twice. So I'm going to denote that by R times R, which is R squared. So let's visualize that. Okay, let's label our vertices 1, 2, 3, 4, 5, and then our action will be R squared. So 1, 2, 3, 4, 5. And then now 3 gets to the top and it goes around 4, 5, 1, 2. So similarly, we can do R cubed and R to the 4. But my question is, what's R to the 5? Okay, R to the 5 should be rotating by 72 degrees 5 times, but that's just 360 degrees. So that's a full circle rotation. So in particularly, or particularly, excuse me, that's, if I label these vertices, I'm sending one around the whole circle and it ends up right back where it started. So in fact, it does that with all vertices, and this R to the 5 doesn't actually do anything. It looks exactly like how it started. So I'm going to denote R to the 5 by E, and I'm going to call it the identity mapping or the identity symmetry. Okay, so let's collect all these together. So E, R, R squared, R cubed, R to the 4. And I want to call that set C5. And actually, this set forms an abelian group. I have to define the multiplication, but the multiplication is composition of symmetries. So just like we saw with R squared, we just apply one symmetry and then the other symmetry to get a multiplication. So indeed, R to the n times R to the m is R to the m plus m, but reduced mod 5. So in other words, rotating by 72 degrees m times and then n times is a total of rotating by 72 degrees n plus m times, but we can ignore multiples of 360 degrees. So we can reduce it mod 5, basically. So actually, you can check that associativity and commutativity are satisfied. I'll let you figure out why that's the case. But the identity element is just that element E that we saw before, the do-nothing symmetry. So when I multiply anything by it, it doesn't change that something. R to the k times e is e times r to the k. And it's just r to the k because e just doesn't do anything. And lastly, for inverses, can you guess what the inverse of r to the k should be? So if I rotate k times counterclockwise, how do I get back to the identity? Or in other words, what element x satisfies r to the k times x equals x r to the k equals e? So you can interpret this as x undoes the rotation k times. You might want to say it rotates k times clockwise, which is a fair interpretation. But we can accomplish this by completing the rotation around the circle, around the full circle. So in other words, we can take x to be r to the 5 minus k. And if we want, we can write that as r to the negative k, which is like rotating clockwise by k times. Okay, so c to the 5 with this multiplication is called a cyclic group of order 5. So that cyclic part comes from the fact that we're cycling our vertices. It's kind of going around in a circle. And the order 5 refers to the size of our set. So there's 5 elements in that set. Okay, so we talked about rotations. Let's talk about reflections. Now I'm going to denote by S the reflection across the vertical line that passes through that top vertex. So we can visualize that. Let's draw a couple pentagons and we'll label the vertices. So now we're acting by S. Now, if I reflect it, 2 and 5 will swap and 3 and 4 will swap, but 1 will stay the same. So notice that if I reflect twice, so S squared, I get the identity back. So one way to interpret that is that the inverse of S is actually just S itself, which is interesting. Okay, but what about other reflections? So let's do some more pentagons and let's call another reflection S prime by a different axis. So we'll label this one and let's look at the line that goes through that vertex 3, for example. So 1 and 5 will swap and 2 and 4 will swap. And I get 5, 4, 3, 2, 1. But actually, that just looks like the same reflection that we had above, but just rotated. Interesting. So if we look at what we had above and then rotate that, then we get our S prime. So start with S, so what we had originally, and then apply R, and we get to our S prime that we just saw. Actually, we could also write this by first rotating 4 times and then applying S. So in fact, S prime is also equal to S times R to the 4. And in fact, any reflection that I want can always be written as our original reflection times R to the K for some K, which is remarkable. And we also get this weird anti-commutation relationship. So S times R to the K is R to the negative K times S. So let's take a look at this latter property here by drawing some more pentagons. So let's just take K to be 2 for simplicity, and we'll make 3 pentagons because we'll first apply R squared and then we'll apply S. So let's label our vertices. So R squared just maps that 1 down to the bottom left. And then we'll reflect along that vertical line. So 2 and 4 will swap, and 1 and 5 will swap. Okay. Okay, but what about r to the negative 2 times s? So r to the negative 2 is just r cubed, since r to the negative 2 is just r to the 5 minus 2, as we saw above. So let's look at that symmetry. So let's do 3 pentagons again, but first we'll do s, and then we'll do r cubed after. Okay, so 2 and 5 swap, and 3 and 4 swap. So we get 1, 5, 4, 3, 2. And then if I apply r cubed, I'm rotating 1 around to the bottom right corner. So at the top, I get 3, and we get 4, 5, 1, 2 in the counterclockwise direction. And that's exactly what we had above. So this is just one example, but in fact, it's always true. And one way to interpret this is that reflecting turns counterclockwise rotations into clockwise rotations of the reflection. So it's kind of a neat little interpretation of that anti-commutation relation. Okay, so let's combine all of our symmetries into one big set. So we have our rotations and this identity, and we also have S, SR, SR squared, SR cubed, SR to the 4, which are all our reflections. And we'll call this set D10. This set has a fancy name. It's called the dihedral group of order 10. Again, order just means the size of the group. But we're lazy, so we usually write it in terms of generators. So these angled brackets means that it's generated by R and S with these relations. So all the words made up of R and S, but simplified by R to the 5 equals S squared equals E, and RS equals SR inverse. So we can reduce any word in R and S to something that looks like something in D10. And if you want to try a little exercise, can you reduce the word R squared S, R cubed S, R to look something like in the set D10 above, using those relations? Okay, so D10 is a non-abelian group since SR is not the same as RS. You can check that for yourself. And in fact, for any regular n-gon, we can make the group of rigid motion symmetries in the same way. We'll call it D2n to be the group generated by elements R and S, so a rotation and a reflection, such that now R to the n is equal to E, but otherwise they're the same. So I encourage you to try playing with D6 and D8, as these are the symmetry groups for the triangles and squares.